Well, good afternoon. This is Wednesday, the 22nd of February, 2:07 in the afternoon. I'm a little late getting started because I had to take care of a couple of things right before class, but I'm the only one in the room, even though it's 7 minutes after class time was supposed to start. So I'll get started without you. I wish someone were here. It's really boring talking to myself. Okay? There are a few announcements, and I'll give you the ones that pertain specifically to my schedule. Of course, by the time you hear this, this will already be over. But this afternoon, as soon as class is over, around 3:15 or shortly thereafter, I've got to leave to go to the Birmingham campus because I've got to take several things to get signed and turn some things in, and also arrange for a vehicle for that part of the signature process too. For Friday, and I'll get to that later. So, in other words, normally my office hours are 3:15 to 5:15. As soon as this class is over, I've got to get my stuff together, which will take a few minutes. Then I'll be leaving to go to the Birmingham campus. Once I get there, I'll be running around to a variety of places, but then I'll get back to my office sometime. I'm guessing around 4-ish, and then I'll be there until 5:15 at least, maybe later, probably later. Okay, so I will have office hours this afternoon, but they'll be on Birmingham campus, not Bessemer, and they won't start at 3:15 because I've got to drive over there and take care of a variety of things, and then when I get back to the office, I'll have my office hours, whatever remains. Okay, that's today. Tomorrow, and I've got to find out when I go over there how they want me to handle this, but if I'm not mistaken, I'll probably have to go over there again. My office hours normally on Thursday are 10:45 till 12:30. I may have to go back to Birmingham campus to pick up the keys to the vehicle I'm driving on Friday. And if I have to do that, then I'll be leaving here shortly after 10:45, get over there sometime around 11:15, hopefully get the keys and the books and everything I need for the vehicle, then come back here and teach my 12:30 class. So I might have half hour, 45 minutes of office hours then, but it's going to be pretty iffy, okay? Then on Friday, last Friday I had an infusion, so I was out all day. I had to be at Kirkland Clinic at 6:30 in the morning, and I didn't leave there until after 4:30 in the afternoon. So no office hours last Friday. This Friday, we're going to Opelika to a math meeting at Southern Union State Community College, and that means that we'll be leaving about 6 in the morning and coming back about 6 in the evening, so I'll be on the Birmingham campus briefly those 2 6 o'clocks, but not much other than that, so I'll be not there during my office hours, 7:45 to 1 at all. Next week gets a little more normal until next Friday again. I have a physical from 8 o'clock in the morning, so that means I'll need to be at the Kirkland Clinic about 7:45, which is when I usually start my office hours on the Birmingham campus. Hopefully the physical won't take more than an hour, hopefully, and if so, then I might be able to get away there around 9-ish, hopefully get back to Birmingham sometime around 9:45-ish or so, hopefully by 10 o'clock anyway, and then I'll be there until 1. So I will have part of my office hours on Friday of next week. This week, none, but Friday of next week, none in the early morning, but I'll be there sometime mid-morning or so until 1 o'clock in the afternoon, or maybe later. Okay, so that catches you up on my schedule. Let's get going with differential equations. Now, according to my mark, we're in section 2.3. Chapter 2 is first-order differential equations. 2.3 are linear equations. And we had just done example 6, and we were about to hit this little blurb called functions defined by integrals. At the end of section 2.2, we discussed that some simple continuous functions do not possess antiderivatives that are elementary functions. And the integrals of these kind of functions are called non-elementary. And for example, you may have seen in calculus that the e to the minus x squared dx is and this integral of sine x squared dx are non-elementary integrals. In applied mathematics, some important functions are defined in terms of non-elementary integrals. Two such special functions are the error function, and it's in your book, but because I'm not certain everybody has it, here we have it. The error function, which is often, let me get my pen back to black, okay. It's called the ERF, error function of x, okay. And it's defined to be 2 over the square root of pi, pretty strange number, okay, times the integral from 0 to x, and that's the variable x there, e to the minus t squared dt. And that was that one that we were just mentioning that was non-elementary function. Here it is with that coefficient. That's called the error function, okay. Now, there's another one called the complementary error function, which is somewhat similar, at least in appearance, ERFC of x, and it starts the same way, 2 over root pi, okay, the integral of x to infinity of e to the minus t squared dt. Okay, look very similar, it's just that they have different limits. The error function is 0 to x, and the complementary error function is x to infinity. Okay, non-elementary functions, but they're used in calculus and in engineering and statistics to some extent, all over the place. From the known results, and you're not expected to know this. In fact, I had forgotten it till I just was reminded of it reading it right here. Here is a known result. The integral from 0 to infinity of e to the minus t squared dt, okay, is equal to the square root of 2 over pi. I mean, square root of pi over 2. Okay, now, oops. Which is sort of strange in its own right, but it is true. They have a little blurb here. This result is usually proved in the 3rd semester of calculus. I don't recall that we've ever done that, but if you've taken calculus elsewhere, you may have done it. Well, I can't get my eraser to come up. Okay, erase too much, but go back and put the 2 in there. Now, notice that is reciprocal of the coefficients of the 2 integrals above. We can write that, so from this result, if we multiply both sides of the equation by 2 over root pi, then that gets it in front of the integral, okay? And so let's do that. Multiply this by 2 over root pi, and this over by 2 over root pi. Okay, these go away, and you're left with 1, and that gives you that formula. Okay. Now, this integral here, which is 1, is a sum of these 2 integrals. Okay. And so the complementary error function plus the error function adds to 1. So this thing plus that thing is equal to 1. Okay? That's sort of the base here. Because of its importance in probabilities, statistics, applied partial differential equations, the error function has been extensively tabulated, and the error function of 0 is 0, one obvious function value. The values for ER f of x can also be found using computer algebra system, CAS, C-A-S. So let's move on to example 7, top of page 60. Erase all that ink. And let's solve a initial value problem, dy dx minus 2xy is equal to 2. Okay? With the initial condition y of 0 is equal to 1. Make sure the door was closed and I wasn't bothering people up and down the hall. Okay. Now, how would we approach this problem? Well, this is a linear equation. There's your dy dx. This is what we call the p of x. That's equal to minus 2x. And our f of x is equal to 2. Okay? How do we approach a problem like this? First thing we do is integrate the p of x. So the integral of minus 2x dx will be minus x squared minus x squared. All right? Okay? Now, what do we do with that? We raise e to the minus x squared. So that gives us looking like something like an error function. Well, that's our integrating factor. So we'll have e to the minus x squared dy dx minus 2x e to the minus x squared y is equal to 2e to the minus x squared. Okay? Now, the way we've done this in the past is say that this is a perfect, this is a d by dx. Too far down, so I think what I'll do is erase this, okay, and start this back up at the top, okay. So this thing down here is d by dx of a product rule e to the minus x squared y, okay. Let's see if indeed that's true. Derivative of this would be e to the minus x squared times the minus 2x. There's your minus 2x and e to the minus x squared times y plus e to the minus x squared dy dx. Sure enough, that's right. And this is equal to 2e to the minus x squared. Okay? Write that in differential form. D of e to the minus x squared y is equal to 2e to the minus x squared dx. Integrate both sides, okay? And this gives you e to the minus x squared y is equal to 2 times the error function, okay? ER f of x, okay? Or at least it looks pretty similar to that, okay? Well, not quite, okay? Still got a little bit to do. If we notice back, the error function is 2 over root pi times this thing. So we got the 2 there, so we need a root pi. So I think your root pi is going to show up right there, okay, times the error function, okay, and then y would be equal to 2e to the x squared, because you're multiplying both sides by that, 2 root pi e to the x squared times the error function. Okay, I think I put the thing in the right place. They factored out the e to the x squared times 1 Oh, I haven't done the plus c yet. Need to do that. And that's, when you do this integral here, let's incorporate in that you could do a plus c, and that would work okay too. So let's just put a plus c. I forgot to do that here, plus c. Now they're doing it slightly different, and we got a plus c here. Okay. Now we know that y of 0 is equal to 1. And that's equal to 2 root pi ERX of 0, and ERX of 0 is 0, so that goes to 6, so C is equal to 1. So now plug that back in, y is equal to 2 root pi e to the minus x squared, no, e to the positive x squared, ERF of x, error function of x, plus 1. Okay? Now, they write it ever so slightly differently. Trying to see. Wait. Sorry. I'm sorry. I kind of blew something there. This part here is the plus c. Okay. And then when you multiply, this has a c, e to the x squared on it, because we multiplied that. I forgot to multiply that in, so now we've done it. And now when we plug in that 1, e to the 0 is 1, so c is equal to 1. So now we write this, the e to the x squared is in both terms here. Okay, and that's why they factor it out. Y is equal to e to the x squared times 2 pi times the error function plus 1. All right, I think that's, yeah. Well, seems like to me they've lost a 2 somewhere. Or I'll put an extra 2 in, I guess is the better way to express it. They have it there. Well, I just have the extra factor of 2. That shouldn't belong. I can't see right now. I think I know where it came from, but it's not a particularly easy thing to undo, so I'll just leave it out for now and say, yeah, this is the answer. Now, I have another little blurb on use of computers. These computer systems like Mathematica or Maple are capable of producing implicit or explicit solutions for some kinds of differential equations using the dsolve, like differential equation solve commands. But since we don't have that, I'm not going into that. Now, there's remarks here that talk about homogeneous and non-homogeneous systems. We've mentioned those before. And I don't see anything all that new there. And then they talk about having a first order differential equation not linear in one variable and linear in the other. And I'll let you read that. We're not going to do anything with that right now. Mathematicians have adopted their own certain words from engineering, which they found appropriately descriptive. The word transient, we mentioned that before. Input or driving function. So these special functions like we run into here can help solve that. It's just another thing. However, I do want to mention this one. The Fresnel sine integral is introduced in problems 55 and 56 in this problem set. You could write on who in the world was Fresnel, or how did he come up with this sine integral, or where are these sine integrals used, what are some applications of them. So there's lots of possibilities there. So move on. This finishes 2.3. So homework exercises here, do any of the odds 1 through 23, any of the odds 25 through 35, any of the odds, well, either 37 or 39 or both, your choice, and then 41, or 43, your choice, or both. There's some discussion problems there, which are not bad to take a look at, and then there's some mathematical problems, radioactive decay series. You can look at that if you want, the heart pacemakers, and computer lab assignments. This is where the sine integral function and the Fresnel sine integral function are mentioned as promised. You don't have to go there, but if you want to use that as a paper topic, you might want to read a little bit about that before you get to it. All right, that was 2.3. Let's move on to 2.4. These are called exact equations. Okay? And what I think oops, that's not what I wanted to do. This is what I wanted. Now, here's another way to write a simple first order equation. Y dx plus x dy is equal to 0. All right. Now you might say, what differential equation is that? That would be dy or x dy dx plus y is equal to 0. Or you could divide everything by x and say dy dx is equal to y divided by x, or plus y divided by x, sorry, is equal to 0, which then is a linear form, and you can solve it the way we were just doing it. Okay? However, this particular kind, especially when written in differential form like this, and by the way, you didn't have to do linear, you could do separation of variables. Dy over y is equal to minus dx over x. Pretty simple to do, okay, and to solve, okay. However, you might want to note this. What if you had an equation, a function that was x times y, and you wanted to take the derivative of that x times y? What would that give you? That would be x times derivative of y plus y times derivative of x. Okay? And if that was equal to 0, that derivative was, well, I'm sorry, we're not going to go there yet. Okay. So this then gives you a way to express the product of a function, okay, by the good old product rule. In this section, we'll examine some first-order differential equations of the form mxy dx, let me make sure I put that, yeah, plus n xy dy is equal to 0. Okay. I hate to do this, but I may have to pause for just a moment. We just have gotten started. I need to run down the hall for just a minute, and I'll be right. All right, sorry about that. I had to, this morning, when I normally have lunch, I had to go to a health screening because they only had a limited time today, and the 45 minutes I have for lunch was the only time I was not in class during that time block. So I had to run down there. Didn't get to, when I got through with it, I had about 5 or 10 minutes, and I was crammed down a salad, probably ate it too fast, didn't drink very much, then taught my last class, and then between that class and this one, ran to my office and crammed down my sandwich and didn't eat very much. And then suddenly I realized I was pretty dehydrated, so I went down to get some water and something to drink, a little caffeine too. And on top of everything, it's really boring talking to myself in a class. So I just needed to take a little bit of a break to go get something to rehydrate. So anyway, now, we sometimes will have functions that look like this when written in differential form. When we do, you can apply a simple test, and that's what we're going to talk about in this section, to determine whether or not that is a differentiable function f of xy. Okay? If the answer is yes, we can construct f by partial integration. All right. Now, the first topic here, differential of a function in two variables. So let's start with this. Let's say z is some function, f of xy. Okay. With a continuous first partial derivative. Now, I was trying to recall De Silva has had Cal 3. Pretty sure. No, De Silva's in Cal 3 right now. And Tanisha, I think you've had Cal 3, so you probably have already had partials. Charles Jennings, I'm guessing you've had Cal 3 since you're in this course. Matt, I know, has had Cal 3. Jonathan, I think, has had Cal 3. Okay? And Nigel has had Cal 3. Okay? So I know that De Silva hasn't yet, and the others of you I either assume have or I know have. Okay? But Cal 3 is when you do partial differentials, partial derivatives. So I know for De Silva and some of the others, maybe you haven't had this yet. So I'm going to do a quick mention of what we mean by partial derivatives. If you have y is equal to f of x, that's a function of one independent variable x. And you can take a derivative of that dy dx, or df dx, however you want to call it. One independent variable. Okay? However, a situation such as this, z is equal to some function of x and y, two independent variables, one dependent variable, then what you can do here is take a partial derivative of each of your independent variables. And it's probably better with an example, and we'll get to one later, but let me just show you what I mean by that. The partial of z with respect to x, that's how we write it. We don't write it straight up and down d. It's this curvy looking d, and that means a partial derivative. Or you could take a partial of z with respect to y. Either one of those. What you do if you take it with respect to x, you hold all the y's as if they're constants. If you're taking the partial of z with respect to y, you treat all the x's as if they're constants, and only take the partial with respect to the one independent variable that you've got there. So this one function, and you could also write it this way, just like in regular derivatives, you could say partial of f with respect to x and partial of f with respect to y. That means the same thing as those two, but you're just taking with respect to one variable at a time. Okay? That's what we mean by partial derivatives. And we will do some examples later, but that's just the general. Okay? So, if you started with z is equal to f of x, y, then taking a derivative, now, z is a function of two independent variables, but if you're writing this in differential form, you can say this is dz is equal to partial of f with respect to x times dx plus the partial of f with respect to y dy. Okay. Now, that's what your dz would be. The change of z as you first change with respect to x, keeping y constant, and then as you change with respect to y, keeping x constant. Okay? That would be, that's your differential equation, you might say, in two variables. And notice the function itself, which is a function of two variables, those are partial derivatives there. Okay. Now, in the special case when this f of x, y happens to be a constant, okay, that implies that this dz was going to be 0. Because if the z is a constant, dz is going to be 0. Okay? That's now the special case that we are going to call exact equations. In other words, given a one-parameter family of functions, f of x, y is equal to c, okay, we can generate a first-order differential equation by computing the differential of both sides of the equality. And here's an example. I think I'll go to a clean page, just because I don't have much room left on that page. Okay? What if you had x squared minus 5xy plus y cubed is equal to some constant c? Okay? And that is something that you could run into anywhere. Okay? This is your function as a function of independent variables x and y, and that is a constant. Okay? X's can vary, y's can vary, but the result of those operations always give you some constant value. Okay? Now, what you can do, just like we did before, is take the partial of this thing here we'll call that f, okay, with respect to x times dx, add it to the partial of this thing f with respect to y dy, and the derivative of that of a constant is 0. Okay, so let's do this. This is what f is. Partial of that with respect to x is 2x minus 5y. Remember, when we take a partial with respect to x, you're taking with respect to that and you keep y as if it's a constant. So minus 5y, that's your partial with respect to x dx. Okay, the partial with respect to y, here you have a minus 5x plus 3y squared dy, and that's equal to 0. Okay, so there would be how that one would break down. 2x minus 5y dx plus a negative 5x plus 3y squared dy is equal to 0. Okay, that's how you would take that function and take, in a sense, a derivative of it, realizing there's two independent variables. And that would be the result. Now, here's a definition. Of course, not every first-order differential equation written in differential form, mxy dx plus nxy. And this does look like an mxy dx plus, this looks like it could be an n of xy dy equals 0. We know the equals 0 is right. Okay. But we don't know if we can do anything with those functions. Sure, this is a function of x and y. Sure, that's a function of x and y. But can we do anything with it? Okay. So for our purposes, it's more important to turn the foregoing example around. Namely, if we're given a first-order differential equation, such as this one, okay, is there some way we can recognize derivative of x squared minus some way we can recognize it. This thing that we've got here, 2x minus 5y dx plus a negative 5x plus 3y squared dy, is a differential d of the top function we have there, x squared minus that. If there is, okay, is there a way, if you're given this, you could go back to that at the top? If there is, then an implicit solution of 3 would be that constant, that this thing here would equal some constant. Okay? So we answer that question after the next definition. So let's clear this so I can write in this definition. It's a little on the long side. So let's say we're starting with a differential equation, or differential expression, okay, not equation, but expression, m of xy dx plus n of xy dy, okay? That differential expression is an exact differential in a region R, okay, of the xy plane, okay, if it corresponds to corresponds to the differential of some function f of xy. Okay, defined in R. Okay, a first order differential equation of the form mxy dx plus n of xy dy equals 0 is said to be an exact equation if the expression on the left-hand side is an exact differential. I'm sorry, is an exact equation if the expression on the left-hand side is an exact differential. Okay. Now, sorry, my head's messed up again. Again, part of this is just because it's so boring talking to myself. The other part is, so far, it's been a pretty long and somewhat stressful, not super bad day. But, okay, a differential expression, m of xy dx plus n of xy dy, is an exact differential on some region R of the xy plane if sorry, it's not having anything to drink. It's sure messing me up. I almost feel like I'm about to throw up, but I don't think so. If it corresponds to a differential equation of some function f of xy defined in that same region R, and that is said to be an exact equation if the expression on the left-hand side is an exact differential. Okay, it almost sounds like you're talking in circles. Okay, it kind of seems like you are, but let's see. So let's go to, let's see, this is not the same one we had before. Here's one. X squared y cubed dx plus x cubed y squared dy is equal to 0. Yeah. They're telling us this is an exact equation. Okay, they're telling us that. Because the left-hand side is an exact differential, and the right-hand side is 0, which then could get to be a constant. Now, why do they say the left-hand side is an exact differential? Okay. Well, what if your function was 1/3 x cubed y cubed, and you took the derivative of that? That would be 3 times 1/3 is 1 times x squared times y cubed dx plus x cubed goodness gracious. 1/3 x cubed y cubed. If you took the derivative of that, you have 1/3 of 3, which would be 1. X squared y cubed. Okay. And, you take the partial with respect to each, and sure enough, you get that very thing. Okay. Now, that was one you could basically do by inspection. Is there some other way that we can test this without that? Okay, and by the way, they wrote this too. I was doing it in my head. D of 1/3 x cubed y cubed would be 3 times 1/3 x squared y cubed. That would be dx plus 1/3 times 3 would be 1 x cubed y squared dy, and that would be equals 0 if indeed this thing were a constant c. Okay, and that's what they get. Okay, now they say here, notice if we make the identification m of xy equal x squared y cubed, n of xy equal x cubed y squared, then the partial, and here's the key, the partial of your m, this being the m, with respect to y, the one that's not by it here, that value right there would be 3 x squared y squared. Okay? And the partial of n with respect to x would be 3 x squared y squared dy. Well, you don't need the dy on it. Okay. Hit the wrong button. Okay. But you see where we left off there. Okay. And you saw that in both cases there, the partial of m with respect to y, let me go back and write them again. The m of xy was your x squared y cubed, and your n of xy was x cubed y squared. If you did the partial of m, that's the ugly m, with respect to y, this would be 3x squared y squared. The partial of n with respect to x would be 3x squared y squared. And indeed, these two are equal. And if indeed they are equal, and that's what the next theorem says, shows that the equality of those partials is no coincidence. Okay? In fact, that's the criterion for an exact differential. So let's get the, this time I need to erase all ink. Okay? Theorem 2.4.1. If m of xy and n of xy, these are two functions, they need to be continuous, okay, and have continuous first partial derivatives. Okay, first partial derivatives, okay. In a rectangular region R, okay, rectangular region R, defined by A is less than or, let's see, they don't put the equal sign, not that it matters that much, but They just don't put them. So inside these criteria, x less than b and c is less than y less than d, okay, then a necessary and sufficient condition okay, that m sub xy dx plus n sub xy dy equals to 0. No, I'm sorry. Just that expression. That's called that expression is an exact differential. Okay. And this is a condition, partial of m with respect to y must equal partial of n with respect to x. Okay? Now, just to sort of get it right, the m is the functional coefficient, you might say, of your dx term. You're taking the partial of that with respect to y. The n of xy is the functional coefficient of the dy term, but you take the partial with respect to n of dx. Okay? Now, they have there a little proof of the necessity side of this. They don't do the sufficient side. They'll do that later, but the condition here okay, and I'm not feeling too well. Okay. All right. Okay. Let's write this, and this isn't, it's not apparently, well, okay. Here's your differential, just like we have up here. I won't write it again. What is this? Now, this is if you have a differential expression f of xy. These are exact for. There exists some function f for all the x's in that range r. I thought I heard someone come in.
Oh. You have a class?
Yeah, I'm here till 3:15. No student showed up.
I'm just looking for hand sanitizers.
Right here, this?
Okay, but you have your own. All right, thank you.
Okay. Cleaning lady came through. Okay. What they say is, let's assume that m of xy and n of xy have continuous first partial derivatives for all of xy. Now, then say we've got the expression here. If that expression is exact, that means there is some function f that for all the x's in that range r, that this thing is partial of f with respect to x dx plus partial of f with respect to y dy. Okay? If that's exact, there's got to be some function like that. Okay. Now, what that indicates is this thing has to be here. M of xy must be the partial of f with respect to x, and n of xy must be the partial of f with respect to y. Okay? If this is an exact expression, then there has to be a function such that makes that true. If that is true, then the m is that relationship to the partial of f with respect to x, and n is that with respect to y. Now, this is something else that we basically learned about with partials. And I realize that Silva and some of the others may not have done partials yet, but here's the situation. Okay? If we take the partial of m with respect to y, that would be the partial of f with respect to y, then with respect to x. So that's basically a second partial there. Well, I'm sorry. Let me write it the same way the book does. That is correct, but they're writing it slightly differently. So let me stick with what they do. The partial of the partial with respect of f with respect to x. So you see, this partial of f with respect to x is what you started with, and you're taking the partial of that expression with respect to y. Okay? And then they say this is d2f dy partial with y, partial with respect to x. Okay? Now, here is the feature of partial derivatives. We know that this is also the partial with respect to x of the partial of f with respect to y, because it doesn't matter which order you do the partials. Okay? If this is our assumption here that the m and the n's both have continuous first partial derivatives for all x, y. If they do, then it doesn't matter which order you take that second partial, and both of these will be this. Well, what is this? This is partial with respect to x of the partial of alpha with respect to y, which was your n of xy. Okay? Let me clean that up just a little bit. Okay. Now, almost feels like we're going around in circles, but we're not quite. Okay? The second partial of alpha with respect to y, then x, is your partial of m with respect to y. Your second partial of alpha with respect first to, with respect to x, then with respect to y, that's your partial with respect to x of your n of xy. Okay, I put the xy there, I didn't in the other places. Well, guess what? If these are continuous, have continuous partial derivatives, that's going to be the case. If there is that f that fits, then this will be the case. So that's going to be the test of whether you have a exact equation or not. Okay? The sufficiency part of this consists of showing that there exists a function for which partial of alpha with respect to x is m of x and partial of alpha with respect to y is n of y, whenever 4 holds. And the construction of those families of functions reflects basic procedure for solving that. So we'll get to that. So let's look at how we're going to do the solution. Okay, let me, goodness gracious. If I can hang on for just about 5 more minutes, I'll make it. My eyes are hurting. I have conjunctivitis in one of my eyes, and it's been giving me problems all week. Hadn't today until now, but it's sort of hard to focus. So, let's say that we were given a equation like this. M of xy dx plus n of xy dy is equal to 0. A linear differential equation, okay, written in differential form, but your two coefficient functions could be functions of both x and y, two independent variables. Okay, that's your situation. Now, given that that does exist, determine whether the equality in 4 that we just did work. In other words, take the partial of m with respect to y, take the partial of n with respect to x. If those are the same, then this is an exact differential. Okay? Now, if that does hold, and it's an exact differential, that means there is a function that the partial of that function with respect to x is your m of xy. Okay? Now, if those two partials are the same, then this has to be true. If that has to be true, what we can do is rewrite this as, I'm going to write it as df equal m of xy dx. Okay? Write it in differential form, and then integrate both sides, and you get f is some function here, and it'll be the integral of m of xy dx plus some, now not constant, but constant function, but some function of y. Okay? It doesn't have to be a constant, it just has to be some function of y alone, because you're not taking the partial with respect to y, you're taking it with respect to x. Okay? So, that f could be some, and we said m and n had to be continuous with continuous first partial derivatives, but now we also have to have they're integrable. Okay? If you can integrate the m of xy and then come up with not a constant, but a constant or a function that is a function only of y, it's treated like a constant, then you have a possible f of xy. And this will be your f of xy will be this integral, well, this thing right here. Okay? Now, that arbitrary function g of y is a constant of integration with respect to x. It can have y variation in it. It's just that your integral only with respect to x. Well, what do we do with that? Now differentiate that with respect to y. You've got this f, do partial of f with respect to y. Okay? And that would be d by dy of the integral m of xy dx. Okay, now, remember, this looks a little confusing, but you've already integrated that. It had to be something that was integrable, so you've integrated it. That's just whatever that integration is, okay? I know it looks messy this way, but that's what you got. And then you're taking the partial of g with respect, or the derivative of g with respect to y, which is just g prime of y. Okay? Now, if this thing is equal to your n of x, n of xy, then we've got it not. Okay? Well, what does that require? That then requires that the g prime of y is equal to n of xy minus the partial with respect to y of your integral of m of xy dx. Okay? And then we just integrate that with respect to y, This is dg dy. So put the dy over here and integrate that with respect to it. And, well, I think I put it in the wrong place. Goodness, this is getting messy. Okay. Whoops. Okay. Okay. This is where my dy goes. Okay. Now, you integrate that, which looks messy, but it's really not that bad because you've already done all the other integrals. Okay, the implicit solution is alpha of xy is equal to c, and you just have to come up with a function. I know we're out of time now. And it says some observations are in order. These are not short observations. So what I think I'll do is we'll stop right there and pick up there next time. Sorry, didn't get to finish at least to the example today. Once we do the example, I think it'll make a lot more sense. Mostly because we've got so many hanging integrals and differential derivatives and stuff. Once you actually do these, they come out making a lot more sense. So hopefully we'll see that next time. Let's see if we got enough to do any homework exercises in 2-4. I think you can do any of the odds 1 through 19. And we'll hold off on doing any past that later. It's basically doing your test. Okay? Identifying what's your m, what's your n, testing to see if partial of m with respect to y is the same as partial of n with respect to x. If it is, then it says solve it. If not, just go on to the next problem. Okay? Any of the odds 1 through 19. All right, sorry. This was a tough day today, mostly because I've been in such a rush. I haven't had a chance to eat or drink what I was supposed to, and now I've got to rush to the other campus. So at some point, it'll all catch up, I hope. So anyway, let's end